Hi, I'm Cosmin, and I'll be talking about our paper on offline hyperparameter selection for offline reinforcement learning, which is joint work with Tom and all the great people listed below. We know that offline reinforcement learning can make RL more widely applicable by allowing us to learn policies purely from log data, and this can be very useful when interaction with the environment is impossible or very expensive. Our paper addresses a major open issue in offline RL. How do you pick good hyperparameters when you cannot interact with the environment? We know that different hyperparameter choices correspond to different learned policies and can have a large effect on policy performance. In order to pick good hyperparameters, we need a way to evaluate these policies and to figure out which ones work well and which ones do not. And the way most recent offline RL papers do this is by running each of the learned policies in the environment. But this approach kind of defeats the purpose of doing offline RL in the first place. Instead, in this work, we look at offline hyperparameter selection, where we evaluate how good each hyperparameter combination is based only on the original dataset. The way we frame the problem of offline hyperparameter selection in this work is illustrated in the figure here. Multiple policies are trained using offline RL or ORL from a given dataset with different hyperparameter combinations. And then the offline hyperparameter selection methods that we use take the same dataset and use it to rank these policies, and then produce a final policy or set of policies that is deemed to have good performance. In order to rank the policies corresponding to different hyperparameters, we need to compute a scalar value for each of these policies. And the way we do this is fairly simple. For each policy, we estimate its value function using some value function estimator, and then summarize that value function using some statistic that brings it down to a single number. In our experiments, we found that the best summary statistic to use was to simply compute the expected value function over the initial states. And we estimate this value function in two types of ways. One is to simply use the critic learned during offline RL training, and the other type of approach is to use offline policy evaluation methods to reevaluate each of the policies using the original dataset. So now for the purpose of assessing ranking quality, we allow each policy to interact with the actual environment, and this gives us an accurate estimate, which we call the actual value in our plots. We can then compare what happens when we rank policies according to these statistics to what happens when we rank them according to their actual returns. And now I will pass on to Tom, who will talk more about our experimental results.
Thanks, Cosmin. We consider tasks with properties known to be challenging for OPE methods. All are long time horizon, most have pixel observations, and the DM locomotion tasks have high dimensional action spaces. For this talk, let's focus on two tasks, insertion and humanoid gaps. Insertion requires control of a robot arm to pick up a block and insert it in a box, and humanoid gaps requires control of a 56 degree of freedom humanoid avatar to leap over gaps. We consider three methods for learning policies: behavior cloning, critic regularized regression, and D4PG. All methods use the same value function update, but they differ in how they update their policies. For behavior cloning, the policy is heavily constrained by the behavior data. D4PG is unconstrained, and CRR is in the middle. We'll show that this has a big impact on offline policy evaluation. In addition, we generate policies with different hyperparameters to generate 256 policies per task. Each policy comes with an offline reinforcement learning critic, but we also reevaluate each policy using offline policy evaluation. We consider one algorithm for offline policy evaluation, fitted Q evaluation. The algorithm uses the same value update as the previous methods, but with a fixed policy. We choose it because it's easy to scale to the tasks we considered. We also ran some additional experiments not included in the paper, where FQE outperformed other OPE methods like importance sampling and model-based methods. Let's focus on one set of results from the paper. The x-axis is the rank correlation between the actual value and the statistics for a set of policies. The columns represent a set of policies generated by different offline reinforcement learning algorithms: D4PG, CRR, and behavior cloning. Let's start with a recent work that looked at offline reinforcement learning estimates with a statistic called soft OPC. They focused on unconstrained RL algorithms in their paper, so we'll start there. And you can see when you take those methods and apply them to these tasks, the correlation is quite low. Now, let's see how correlation improves as we make different design choices. If we look at the behavior-constrained policies, already correlation significantly increases. If we look at using OPE estimates with the same statistic, performance increases further. Now, let's look at offline reinforcement learning estimates with a different statistic, the expected value of the initial states. And you can see sometimes this performs better, but sometimes it performs worse. Finally, let's look at OPE estimates with that same statistic. Here we can see that it performs much better, especially for constrained policies. In that setting, the correlations are around 0.8 to 0.9. These trends appear across the tasks we considered. And to us, this really highlights that little design choices can make a big difference when ranking policies. Of course, there are limitations. In this work, we didn't ask the meta question of how to choose hyperparameters for fitted queue evaluation. We didn't look at the effect of dataset size or the behavior policy. And we only evaluated things in simulation so far. In summary, online hyperparameter selection is infeasible for offline reinforcement learning. But we found a simple setup that works well for offline hyperparameter selection, using fitted queue evaluation and behavior-constrained offline RL algorithms, and a simple statistic. This setup works well for high-dimensional control, pixel observations, and long time horizons, and works significantly better than some recently proposed methods. Thank you very much for listening, and check out the paper for more details.